Okay, so I don't really prefer to make videos for biochemistry because I think a lot of them are already on the internet. Kevin Ahern, MOOF University. However, there are just certain little things here and there that I feel like would be better represented in a concept map, and so that's why I'm doing this. The first thing that I want to talk about is for enzymes. So for the first exam material, with the exception of a few things, that was pretty much a review of general biology, general chemistry, and organic chemistry, kind of all merged into one. But for enzymes, there's the things that I'm going to mention here are the thermodynamics of these reactions, and lastly, other factors that can play into roles, mostly just cofactors. So just in case you don't remember, but reaction coordinates depend on the change in the Gibbs free energy, the delta G, whether or not this value is positive or negative. So the way that we define delta G is this is equal to delta G naught, this is a Gen Chem concept review, I know, plus the ideal gas constant times the temperature times the natural log of your product concentration over your reactant concentration. Now, this is an enzymatic reaction, so it's not like we have 2 or 3 coefficients, but if there were coefficients, we would raise them to that power of those coefficients. So this is the generalized equation for Gibbs free energy, and if this value here, if the delta G here is positive, or if the delta G is negative, that can severely influence your kinetics. So if it's a positive delta G, then this reaction is not spontaneous. It's not spontaneous, it does not happen, and it does not increase the entropy by a direct relation there. If it's a negative value, however, it is spontaneous. So, some other notes that we're going to make about this, and I'll talk about spontaneous versus non-spontaneous a little bit later, but for enzymes, in the context of this, all that they do is they lower the activation energy. And you can think of this in relation to thermodynamics, but you can also think of this in relation to kinetics, which we'll talk about much later. But know that enzymes just lower the EA. Okay? They lower the activation energy, but they do not change the laws of thermodynamics. They have no effect on this. Okay, so what we use, because this is a generalized general chemistry equation, and we don't really use this at various atmospheres of pressure, right? We have the R, the gas constant here. We don't really do this at various atmospheres of pressure. We don't do this at various volumes. We don't really do this even at various temperatures. So we have one that's really unique to the cell physiology, and we just go ahead and substitute that in for at room temperature and at 1 atmosphere pressure. And the only thing that we're really worried about is the KEQ, which, if you remember, K is defined by, for any reaction, K is just that, products over reactants as a concentration. So we can go ahead and represent our equilibrium constant, the KEQ, for cellular conditions as anti-natural log raised to the negative delta G value, negative delta G naught, sorry, divided by 2.47. This is given to us as a representation of the temperature and pressure at which these things take place in. So let's just kind of talk a little bit about, as a review for general chemistry, spontaneous versus non-spontaneous reactions. So delta G, negative delta G means that we have a spontaneous reaction. So if we were to use, and it doesn't have to be a chemical reaction, it can be a physical reaction or physical phenomenon. So we're going to keep it really simple, and I'm going to use the analogy of me dropping this pen here as I do that. So as I hold the pen up high, I have the pen here, say, this is the energy, this is high energy, and this would be low energy. So I'm holding it up here, it's at a very high energy state, it has a lot of potential energy, and as I drop the pen and it falls, it goes down to a low energy state, and in the process, that potential energy that it had up here was converted to kinetic energy. So we started off in a very high energy state. We still had to put energy into the system for it to take place, but at the end of the day, we're in a lower energy state than we were before. This would be our reactants here. This would be our products here. This line between here, I can draw this right here. This right here, this is the EA, the activation energy. Everything between here, this is the transition state. And then that right down here we have the product. So if we were to say that this is, high, say this is 10, and the low energy state is like a 3. Okay, so if we take the delta G of this, the final 3 minus the initial 10, we get -7. Okay, so energy has been released from the system into the surrounding. Energy is being further spread out. If we have further energy being dispersed or spread out, we have an increase in the microstates. We have an increase in the overall entropy of our reaction. So that's what a spontaneous reaction would look like. If I were to just go ahead and draw this over here, on this axis we have energy. Over here we have the reaction coordinate. I'm not really so worried about that. But for a non-spontaneous reaction, as you can imagine, if dropping the pen was a form of a spontaneous reaction, then if I throw the pen up, that's a spontaneous reaction as well, which ultimately will end up in falling it right back down, right? Because you can't go against the laws of thermodynamics. So for a spontaneous reaction, we have ourselves the reactants, which are down here, and I'm going to throw them up. They're going to go from a low energy state, there's still a transition curve that we have to deal with, to a higher energy state. And again, the differences between these two here, this thing here, this is my EA, then there's a transition state here. But the reactants and the products are in a higher, the products are in a higher energy state than the reactants. So say, for example, the products are 10. So if I take, say the products, are 3, and the initial energy concentration was like that of 10. If I go ahead and do this and subtract the final minus the initial, so my final was a value of 10, my initial was a value of 3, well, that's going to give me positive 7. So this reaction is spontaneous with regards to that. And the same axis, energy, and then down here I would say reaction coordinate. I just don't have room to write that out. So that's it for the thermodynamics of reactions, spontaneous versus non-spontaneous. I'm assuming that you know about entropy and the second law of thermodynamics. That's a Gen Chem and physics thing if you really want to get into it, and hopefully you have read at least Brian Greene's novels because they're amazing. Anyways, so for cofactors, there's 2 types of cofactors. There are the metals. These tend to be cations. And then there are the coenzymes. So the coenzymes tend to be vitamin derivatives, or you could just say that they're organic compounds. They're pretty straightforward. So for the metal cations, this includes things like magnesium or iron or things like that. For the coenzymes, though, there's 2, subcategories that we have here with these. There's the prosthetic groups and then the co-substrates. The co-substrates. So, in case you didn't already know this, and this is a general biology thing. Everyone in general biology should have talked about cofactors at some point. But what cofactors do is they bind in the active site, and when they bind to the active site of that enzyme, they make the enzyme a more conducive environment for the reaction to happen. Okay, so prosthetic groups. In this context, the vitamins or organic compounds that act as coenzymes, prosthetic groups are the ones that are going to be bound very tightly bound to the active site of our enzyme, which again, I'm making the assumption you know that already. And then the co-substrates are loosely bound. That's why we call them co-substrates. Loosely bound to the active sites of our enzymes.